Welcome back to Calculus 2. This will be our last video dealing with convergence tests. We're actually not going to introduce any new convergence tests in this. We're just going to talk about a new definition, a new theorem, and then just do a bunch of problems. We've already mentioned this before in passing, but here's the formal statement. A series is conditionally convergent if it is convergent, but not absolutely convergent. So, for example, this series is conditionally convergent if you do the alternating series test. This does definitely go to 0. It is definitely decreasing for all n greater than 1. And this 1 over n's are all positive. So it does converge. But if it's not alternating, this is the harmonic series, which does diverge. So you need that alternating series factor for it to converge. This is conditionally convergent, not absolutely convergent. It's a small distinction, but it's one we'll generally be asked a lot in exercises. This is the rearrangement theorem for absolutely convergent series. It says if you have a series that converges absolutely and you rearrange the terms, both series, the original series and the series with the terms rearranged, is still going to converge to the same value. You might think, well, hold on, wouldn't that always be true if you have a convergent series? No. If you have a conditionally convergent series, you can rearrange the terms and get different limits. To see an example of that, there's one on page 614 in the book where they take the harmonic series, rearrange the terms, get a different limit. So yeah, it's an interesting thing. It's really a consequence of doing an infinite sum. When you take sums to infinity, you can make a lot of things happen. But that's really all of the theory for this section. The last thing we're going to do is we're just going to do a bunch of converge or diverge problems. Just for review, here's everything we've used to determine the convergence or divergence of a series. By far the easiest test is the nth term test. If you look at the limit of the sequence of terms and it's not 0, anything but 0. A finite limit, infinity, or just no limit, the series diverges, full stop. If you recognize that you have a geometric series, those are pretty recognizable. That would then converge if you have a common ratio that's less than 1. Otherwise, it's going to diverge. We actually did a proof of that. If you got a p series, p is greater than 1, it converges. Less than or equal 1, it diverges. Dealt with one of those in the last video, I think. Series with non-negative terms. We've got a bunch of tests for that. The integral test, comparison test, limit comparison test, ratio and root test. Work just fine as well. If you have some negative terms, well, you can take their absolute value and then do all of these. If it's alternating, then you can try the alternating series test. This is almost the sequence I would go in to check a series as well. These are all good things to check because they're pretty quick. Nth term test, of course, is usually the fastest, but all of these, honestly, the top 3 are all really simple, but they're all very specific. This one you might have to do a little bit of a problem to make it happen. These you won't have to do that much manipulation to see whether they fit these or not. But let's do some exercises. Alright, our first exercise is this problem 26. See, we have negative 1 to the n, and then the nth root of 10. Well, what happens to 10 to the 1 over n? That is going to go towards 1. So negative 1 to the n times 1, well, times 10 to the n, 1 over Negative 1 to the n times 10 to the 1 over n is going to go to doesn't exist because it's just going to alternate. So this is going to diverge by nth term test. It doesn't really work with the alternating series test because it doesn't go to 0, so you can't really use that. So honestly, this is a good thing to start off doing, is see whether the expression without the negative, if you do have the alternating series thing, goes to 0. If it does, well then you might want to try some other things. If it doesn't, you can stop there, because the nth term test says it diverges. Alright, this one, still alternating. If you look at... If we just looked at 1 over n squared plus 2n plus 1, ignoring the negative 1, I'm pretty sure this is convergent, because this would be equivalent to, say, a p-series of 1 over n squared. You multiply up the n squared, limit as n goes to infinity. N squared over n squared plus 2n plus 1. So this would go to 1 either by L'Hopital's rule, or you could divide top and bottom by n squared. Either way, you'll get the same result. So this is going to converge absolutely by limit comparison test. Because since 1 over n squared converges, so must this, since they went to a finite value. Other things that might work. You could probably do a ratio test on this. Well, no, I think ratio test would be inconclusive. I mean, I'm sure you could do a direct comparison. Oh, yeah, I mean, you could do alternating series test on this. Sure, it does go to 0. It does eventually become non-increasing. That'll tell you it converges. Sure. Generally, though, on all of these, I'm going to check for absolute convergence just to see. So cosine n pi. This is not alternating. Or is it? Let's see. 1 pi, 2 pi, 3 pi, 4 pi. Yeah, it actually is alternating. I didn't really think about it because it doesn't have an alternating series factor, but it does alternate between positive and negative. That's kind of interesting. It would be basically this. Let's see. Cosine of pi is negative. So it would be... The first one would be negative, so negative 1 to the n equal 1 to infinity. If you wanted to write this in proper form, be cosine n pi in absolute value over n. And cosine n pi is just going to flip between positive and negative 1, because cosine of pi is negative 1, cosine of 2 pi, negative 1, is positive 1. So it's just going to flip back and forth between negative 1 and positive 1. The bottom is going to get 0. In fact, I didn't even really notice. That's kind of funny. This is basically equivalent to n equal 1 to infinity of negative 1 to the n over n, because, I mean, that's all it's doing. This is just always 1. So it's negative 1 to the n. It's the conditional. It's conditional convergent. You can tell it's convergent just because this is going towards 0 and it'll eventually be infinitely small. But convergent by alternating series test. I'm just going to say AST. Only conditionally convergent, I think. Because if you remove the negative 1, it's 1 over n, and that's a divergent p-series. or the harmonic series is what we call it. That's cute. Is problem 40. This one's just pretty busy. It does have an alternating series term. First thing I think I would do here, probably just ignore that, maybe. Let's see what the ratio test would do. Ratio test is usually pretty good for factorials. If I do n plus 1 factorial to the 2 over... That thing on the bottom is very interesting. I wonder if I can simplify that in some way. I don't know. Over 3 to the n plus 1 over... Let's see, add 1, it would be 2n plus 1, so it would be 2n plus 3 factorial times 2n plus 1 factorial, because you flip this and multiply, times, just do a little bit of labeling there so you see what I'm pulling from, over n factorial squared, 3 to the n. Yeah, I guess this way I don't necessarily have to mess with the factorials that much. This will just be n plus 1 squared, because the n factorial part squared will cancel out. So that's nice. N plus 1 squared over. On the bottom you'll have 2n plus 3, and then 2n plus 2. Because, yeah, the next one will then be 2n plus 1 and all the way down, so 2n plus 1 factorial. So that'll cancel out. And then we just got the 3's to go, so that's easier than the factorials. That's just going to leave us a 3 on the top. Limit. Okay, so we basically have a rational expression, 3 times n plus 1 squared over 2n plus 3 times 2n plus 2. A rational expression will just go to its leading terms, leading coefficients. A rational expression will just go to its leading coefficients over each other as n goes to infinity. So that's just going to be 3 over 2 times 2, 4. If they have the same power, which these do. Squared on top, squared on bottom. That is less than 1. Our rho is less than 1, which was the condition for absolutely convergent. That's interesting. I had no idea looking at this whether it was going to be convergence or divergence. I didn't really have a sense for. I knew this is a lot larger than n factorial, but I wasn't sure if it was large enough to beat n factorial squared and multiplied by that exponential function. But apparently it was, so absolutely convergent. That's a short little end to this section. I just wanted to do some more problems, really. Next time, we'll move into power series. A very important section of Calc 2. In fact, I would probably spend a week or 2 weeks just on this and its subsequent couple sections if I had time. Unfortunately, the way this semester is going with all the COVID stuff, I'm pretty strapped for time, so I think we're going to cut it short on the first 2 sections. So I'll add more later. Have a great day. See you in the next video.